As we did with systems in which we're looking for the forces, when we're interested in energy, we want to distinguish the system and distinguish it as being separate from the environment. So our system here is the object or set of objects that are acting together, whose motion we're interested in, and we're looking at that system, how the system changes for itself, and how that system interacts with its environment. Within a system, energy can be transformed from one type to another. We'll see a little bit more about this, but we've talked about kinetic energy from motion, several types of potential energy, as well as thermal and chemical energies. And so these different energies can be interchanged within the system. If the system is not interacting with its environment, then we would say that the total energy of the system is unchanged. In that situation, we would say that the change in energy is zero, and thus the energy is conserved. That is to say, all the energy that's there at one point of time would still be there at another point in time. If we have a process that transfers energy to or from the system by mechanical means, that is called work. By mechanical means here we mean forces being applied to the system. So for example, if you have brakes on a car, those brakes are applying friction to the system and are applying a decelerating force and would be taking away the kinetic energy of the car by slowing it down. We can also have processes that transfer energy by thermal means, and that is called heat. We see that a lot more when we get into thermodynamics in later modules, but in those situations we can have a hot object or a hot part of the environment can raise the temperature, add energy to a system, and that can be used to do work or to otherwise change the system. We said that energy can be changed within a system, or work can be done to add energy to the system or take energy out of the system to or from the environment. One example here is putting a shot. The shot put is an Olympic event where an athlete throws a small metal ball. In this situation, work is being transferred into kinetic energy. Basically, the athlete is doing work on the shot. He's applying a force to it with his arm and pushing it over a distance as he extends its arm. So that athlete is doing work, and as he does this work, as he pushes the shot put, it goes faster and faster, and thus it gains kinetic energy. So this is an example of the environment. The athlete is the environment, is doing work on the system. Another example of energy transfer is pulling a slingshot. In this situation, external work is done to increase the spring potential energy of the system. In this case, the slingshot itself is the system, and the child playing with the slingshot is the environment, is outside of the system. Here the child does work by pulling back on the rubber band and stretching it out. By doing so, he gives it potential energy. When the child releases the rubber band, it snaps back to its regular length and releases that energy, shooting the projectile out of the slingshot. A falling diver is an example of potential energy being converted to kinetic energy. Here, when the diver jumps off of a cliff, the diver initially has gravitational potential energy at the top of the cliff. He has that gravitational potential energy as part of being that high up off the ground. After he jumps, he falls downwards, and so he's losing that gravitational potential energy. But as he falls, that gravitational potential energy is converted into kinetic energy that's downwards. This is a parallel between the conversion of gravitational potential energy into kinetic energy that parallels the acceleration of gravity causing him to speed up, causing his velocity to become larger. So here we have gravitational potential energy being turned into kinetic energy. And to comment here, gravitational potential energy is the potential of gravity to do work. Technically, gravity is external to the diver here. Gravity is due to the Earth. And so what's happening is that he must have done some sort of work to get high up on the cliff and to gain that gravitational potential energy to begin with. He must have done some work to walk up there or to ride a trolley up there or something like that. When he jumps, gravity is actually doing work on him to fall downwards. And so in that case, gravity can be thought of as an external force doing work to increase the kinetic energy of the man who's the object. But we treat gravitational potential energy as part of the object's energy here. Basically, we're treating it like a check. The idea that when you have a check, you don't technically have the money, but you know you'll get the money when you need it. The same way here, if you have gravitational potential energy, you don't technically have the energy right now, but you know that if you jump off the cliff, if you start heading downhill, you'll gain that energy back because gravity will do work on you as you go back down. The final example of energy transfer that we'll consider is for a speeding meteor. In that case, a meteor is falling into the Earth's atmosphere at a very great rate of speed. And in that situation, the meteor has a large amount of drag, and so that drag is a force of friction, and that force of friction is going to take away from the kinetic energy of the meteor, and it's going to convert that energy into thermal energy. It's going to heat up the air around the meteor, and it's going to heat up the meteor itself, causing it to partially melt. And so in that sort of situation, when we have a friction-type force, the kinetic energy is siphoned away. It's transferred into thermal energy, which is one way to account for that lost energy. Thus, we've seen several types of typical energy transfers. We see that these energy transformations within a system, they move the energy around, they change the form of the energy, but they don't change the total energy of the system. The total energy of the system is conserved in a closed system. Change occurs only when there's a transfer of energy between the system and the environment. So when you have work done where energy is being added to or taken away from the system, is when you have a change in the internal energy of a given system. Typically, incoming energy is treated as positive, and outgoing energy is treated as negative. From that, we can simplify to say that the change in energy of the system is equal to the external work done, or the work done by external forces. If there are no external forces affecting the system, then the change in the energy of the system is zero, and energy is conserved. If there are external forces, and those external forces can either increase the energy of the system by doing work, or they can decrease the energy of the system by taking energy out of the system. This is the energy principle that we'll be studying in this module. Just to recap our study of energy, we consider a system that has internal energy of different kinds, and that system may be in contact with the environment. Inside the system, energy is transformed without loss, so that the energy is conserved within the system, especially in a closed system. However, sometimes you can have energy being added to the system in the form of positive work being done, or you can have energy be taken out of the system in the form of negative work being done. In that case, the energy is transferred to or from the system. In that case, we don't have a closed system, and energy is not conserved. When we're looking at the work done on the system, external forces are the things that transfer energy to or from the system. Positive work means energy is added to the system, and negative work means that energy is being removed. In an isolated system, one that's not in contact with its environment, we say that energy is conserved. So that typically the change in energy of the system is the external force. For a isolated system with conserved energy, we can simplify that to say the change in energy of the system is zero because there are zero external forces to do work on our system. If that's the case, then the energy at some initial point must equal the energy at some final point.